So there's another thing to consider when we're talking about energy, and that is the concept of power. So the energy, when we're using up energy and transforming it from one form to another, there is a time it takes for that to happen. So this rate kind of depends on a certain number of things. So let's say your muscles are transforming chemical energy that you have in your food into kinetic energy. And they would do that faster if you're running up a set of stairs than if you're walking or up the stairs instead. So whether we walk or we run up the set of stairs, though, our body applies the same force against gravity and travels the same vertical distance. In other words, we do the same amount of work, but the rate at which we do the work is different. It depends on how fast we move. So power is what we use to look at the rate of how energy is used. And it is given the symbol P, capital P, but it is measured using watts. Power is a scalar quantity as well, so it doesn't have a direction associated with it. It is the amount of energy used up or the amount of work done over a period of time. Watts are equal to a joule per second, and you can convert that to other SI units. But it's generally, you can always consider power is how much energy we use per unit time. So here's a quick question. It says, how much energy does a swimmer produce if the swimmer transforms 2.4 kilojoules of chemical energy into kinetic energy and thermal energy in 12.5 seconds. We don't actually need the paper to calculate that. We can just use this calculator here. So it was 2.4, so I'll write 2400 kilojoules, right, or 2.4 kilojoules in 12.5 seconds. It is 192 watts, but we need to round to two significant digits, so we have 190. A 64 kilogram student climbs from the ground floor to the second floor of his school in 5.5 seconds. The second floor is 3.7 meters above ground. What is the student's power? Well, we'll just do this totally with the calculator. Let's see what the student did here in terms of how much energy they've used up. To go to that second floor, it would be that distance, the height that they've traveled, times g, times their mass, which is 64. So this is the energy. If they did that in 5.5 seconds, we divide by 5.5, and we get about 420 watts. Okay, next question, or next thing to look at here, we have, like other electrical energy transforming devices, electrical devices may transform energy quickly or slowly. So the rate at which an electrical device transforms energy is sometimes referred to as the device's power rating. So if we rearrange the power equation, we can get the equation delta E equals PT, which can be used to calculate the amount of energy transformed by a device. We will look at electrical power. It's calculated a bit differently, but it's the same. The watts we use for electrical energy and the watts we use for mechanical are actually the same watts. It's just that we can calculate them using different physical quantities. This question here says we have the Pickering nuclear power plant has a power rating of 3,100 megawatts. How much output energy can the generating station produce in one day? So it's a two-part question. The first part is simple enough. If we write down 3100, that is how much, that's our power rating. We have to multiply that by 24 hours and multiply that by 60 minutes and multiply that by 60 seconds. That gets us to 267,840,000. And that's equivalent to 2.7 times 10 to the power of 8 megajoules, because we started with megajoules. So it's a significant amount of energy we can generate in a day. Let's look at the second part of this question. If the power plant is 38% efficient, how much input energy do we require? Well, this is how much energy we produce based off the power rating. In order to find out how much energy we had to put in, we have to divide this by the efficiency. So divide this by 0.38, and we get 842,105. And if we round that, we get 7.0 times 10 to the 8 megajoules. And lastly, how much energy in megajoules is lost? Well, we'd have to subtract those two. So the subtraction you could also just find 62%. So let's do it this way. Because I have this value here, if I multiply this by 62, 0.62, I'll find out how much energy is lost, which is 437,002,105. So 4.3 times 10 to the 8 megajoules of energy is lost.